Welcome to Darjil Learning Hub. Dear friends, in this episode, let us see what is the basic concept of linear algebra and its applications. In the previous episodes, we saw what is vector space, what is subspace, what are called span and linear combination, linear independent, dependent, everything we have seen in the previous episodes. Now we shall see the important topic which is given in vector space, which is dimension and basis. Basis and dimension we shall see in this episode. So before starting this episode, I can tell you what is vector space, subspace. Vector space, a set or a field DF together with the two operation having 8 axioms, and also subspace. In the second episode we saw what is subspace. Subspace means basically it is a subset of a vector space, and then it holds 3 conditions. One is 0, x plus y, scalar multiplication. If so, it is subspace. Similarly, we in the third episode we saw what is span, what is linear combination, what is linear independent, dependent. And then with this we can wind up this section of the first unit of electronics and communication engineering. This is the last topic of their first unit, which is basis and dimension of vector spaces. So we shall see first of all what's the definition, which is called a basis. A basis beta, just we are giving a name, that's a basis beta for a vector space V, is a linearly independent subset of V that generates V. So in the previous episodes we saw what is called a linearly independent set. Linearly independent means it's a linear combination with the scalars. All of its scalars where 0 means then the vectors are called linearly independent. So the basis for a vector space is a linearly independent subset of V that generates V. So that itself is the collection of linearly independent subsets. If beta is the basis for V, we also say that the vectors of beta form a basis for V. See, beta basis means that beta form a basis. Basis means what? It generates linear combination, linearly independent subsets. So linearly independent subset means automatically the linear combination with the scalars are all 0. So or explicitly we can say a set S equal to U1, U2, etc. U1 of vectors is a basis of V if it has the following 2 properties. S is linearly independent and the linear combination is nothing but the superset. So if the 2 properties are okay, means we can call those vectors are the basis of the given vector space. Once again I am repeating, a set S will be call it as the basis of the given vector space if that S satisfies, if that S should be linearly independent and the linear combination of those vectors is nothing but the superset. If so, we can call this is the basis of these vectors are the basis of the given vector space V. So in the second definition we shall see what is called dimension. So these are the 2 topics which we are going to learn. The first topic which is basis over. Now it is vector dimension. What is its dimension? Vector space is called finite dimensional if it has a basis consisting of a finite number of vectors. So if it has a finite number of vectors means it is called a finite dimensional vector space. The unique number of vectors in each basis for V is called the dimension of V. The unique number of vectors in each basis for V is called the dimension. Clear? So dimension is called what? What is called a dimension of the vector space V? The unique number of vectors in each basis. It is denoted by dimension. Dimension, the short word dimension, DIMENSION is dimension. So here the dimension is denoted by dim of V. So with this information, let us see the problem. The first problem is the set of all n by n matrices having trace equal to 0 is a subspace of W. Before that, I can show you some of the examples also, so that definition of dimension will more clear. So here dimension is denoted by dim of V. This means dimension of the vector space V. So the vector space is 0. Singleton set 0 has dimension 0. 0 is the unique element, so the dimension is also 0. The vector space with the n tuples, Fn means n tuples of F has dimension n because it has n set of vectors. The vector space of matrices with the m rows and n columns of over the field F has dimension m into n. This is very important, m, the product of m into n. And the vector space of polynomial set has dimension n plus 1 because even in polynomial set also, if it is P1 means your expression is 1 plus x. So P1 has two entries, two terms. So P2 is what? 1 plus x square. P2 having 3 entries. So automatically Pn having n plus entry. Therefore, the dimension of the polynomial set is n plus 1. Dimension of the collection of matrices is m into n. The dimension of Fn, that is n tuple F is n, and the vector space with the singleton set 0 has dimension 0. So these are the examples of the term which is called a dimension. So we shall see the first problem with the n by n matrix. N by n matrix means rows, n rows and n columns, both n number of rows and n number of columns. That means it is called a square matrix. A matrix with equal number of rows and columns are called a square matrix. So that is the meaning of the term n by n. N by n means n rows and n equal number of rows and equal number of columns. So matrix is having trace equal to 0. Trace means what? Some of the diagonal, principal diagonal elements are called trace. So for example, I can consider one matrix with the 3 by 3, order 3 by 3, D, E, F, G, H, I. So this is what the principal diagonal elements A, E, I are the principal diagonal elements. If the trace of this particular matrix A, TRAC, trace of this A is nothing but, or trace is given as A plus E plus I. This is what the trace of the given matrix A. So find the basis for W. What is the dimension of W? So this is what the given a collection of matrices. We will find out its basis and the dimension. So we shall see the proof. So dimension trace of n by n matrix means it is the sum of the base principal diagonal elements. So because you know here it is denoted as m11, m22 etc. plus mnn, because you see, if we will consider a matrix means, if I have shown A is equal to 3 by 3 matrix means A, B, C, D, E, F, H, I, J. So there it is a 3 by 3 matrix, 3 rows and 3 columns. You know, this is what the element which is present in the first row, first column. First row, second column. First row, third column. This is second row, first column. Second row, second column. Second row, third column. Third row, first column. Third row, second column. Third row, third column. So while looking, the diagonal elements are denoted as first row, first column, second row, second column, third row, third column. That is in the principal diagonal. So bases are same. That's why trace means sum of the principal diagonal element. That's why here the definition it is mentioned as M11. That means first row, first element. M22 means second row, second element, etc. Nth row, nth element. That is the sum of diagonal elements is denoted by this notation. It is what called a trace of the given matrix M. So now let us see trace of M equal to 0 is a subspace of W of M by N F. So because while telling this a subspace means we have to find three condition. Now basically it is given that it is a subspace of 0 having, x plus y having, cx having. So trace of M equal to 0 is a subspace of W of M n by n matrix. Consider a vector space V and a subspace W defined as the set of all n by n matrices having trace equal to 0. So we shall find the basis for W and the dimension of W. This is what our question. So considering this vector space with the traces, we will find its basis and the dimension. So see W, in general case we were writing, let us take the matrix with the n rows and n columns denoted by A11, A12 etc. A1n. Similarly, A21, 22, etc. to n, it is a n by n rows with n columns. So see, there are n rows. The last row is n1, a n2, a n3, a n4, etc. a nn. This is what the last row with the condition which is given in the question itself, trace is equal to 0. So what is the trace of this n by n matrix? A11, A12, etc. A1n. That's why it is here written as A11 with the condition of this n by n matrices A11 plus A12, A22 plus etc. Ann equal to 0. So in the dimension of the vector space, already we saw immediately after the definition of basis and dimension, I have given an example. The collection of matrices with the m rows and n columns over the field F. The dimension of this matrices m into n. This is what we saw. Here the matrix with the n rows and n columns. So automatically what is its dimension? N into n, that is n square. That's why it is written as, and the dimension of the vector space M with the n rows in n column is n square. Assume A is an arbitrary element in the subspace W and A is given by, we can choose an arbitrary element in the subspace of W. Let it be A is equal to A11, A12, etc. It is an arbitrary element in W. We observe that there are n diagonal entries which satisfy A11, etc. A1nn equal to 0. See, for example, we can choose the first column. So this is, from this n by n matrix itself, we can choose n diagonal entries. N diagonal entries means, for example, if it is 2 by 2 matrix, 1 diagonal. Next 3 by 3. Next 4 by 4. Next 5 by 5, etc. n by n. But all which should satisfy this trace condition. This can be written as Ann is equal to, bring the remaining terms to the RHS. It is minus A11, minus A12, etc. Taking one minus outside, we will be getting n equal to I equal to 1 to n minus 1, because nn till 1 to nn we are having, ann is already there. So the rest of the elements were an minus 1, aii. This is, call it as equation number 1. And we will put that in the given equation A. We will find A11, 1 to etc. 1 n minus 1 etc. 1 n. Similarly, we will find this equation. Instead of A n n, see, in the previous one, the last term is ann. So here is the place we can substitute ann as minus of a1 1, a12, a11 minus a22, etc. minus an minus 1, an minus 1. An minus 1, n minus 1. This is what we have to substitute in the place of ann. So we'll be getting, this is what we have substituted in the place of ann. So then from this we can taking a11 outside, we will be getting this. Then n minus 1 plus etc. n minus 1, n minus 1 outside. So the second term a22, take it out, you will be getting another element, another matrix. Similarly, n minus 1, n minus 1, you take it out. So remaining you will be getting the element, all entry 0, it is 1, this is minus 1. Correcta? Plus the remaining a elements, I equal to j equal to 1 to n, not equal to j. So remaining entries where we were put it generally like this, where Eij is a n by n matrix with 1 is in the I and j entry and 0 elsewhere. I and j entry only, the element becomes 1, the remaining entries were 0. Clearly every element of W can be written as the linear combination of the set beta 1, see, first entry, last entry minus 1. Similarly, etc. Then second entry, last but the previous entry, second entry 1, last but the previous entry minus 1. And then third entry 1, last but the previous third entry 1, minus 1, etc. See, the last two, 2 by 2 place 1 and minus 1, where Eij, I not equal to j, I varies from 1 to n. This is a general case we were writing. Clearly beta is the span W, also beta is the linearly independent set, because the remaining entries are all 0. So automatically when we form a linear combination of these vectors, automatically the only two elements were present, one is positive, negative. So if you choose A with 1 and a1 b with minus 1, a plus b, automatically a minus b 0. So each entry, all the entries were, all the scalars were 0, automatically we can say it is a linearly independent set. Therefore beta is a basis for W. Similarly we can find its dimension. Note that in the basis set beta there are n minus 1 matrices which satisfy the condition that the trace equal to 0. What is trace? Sum of the diagonal principal diagonal element is equal to, and there are n minus 1 into n equal to n square minus n matrices which have 1 in the ij entry, 0 elsewhere. Only 1 present in the ij entry, the remaining or all entries were 0. That is the meaning of this term. We know that in general the dimension of a vector space V is defined as the unique number of vectors in each basis of V. That is a theorem which we have seen. Here the total number of matrices in the basis beta is, see, 1 plus 2 plus etc. up to n is what? N square minus n plus n minus 1. This is what n square minus n means, n minus 1 into n plus n minus 1. These are the total number of matrices in the basis. N into n minus 1 term plus n minus 1 term. So simplifying, n square minus n plus n minus n cancel, n square minus 1. Hence the dimension of the given subspace of W is n square minus 1. So beta is the basis of this m n by n matrix with the trace 0, and the dimension is n square minus 1. Now the next problem is determine which of the following sets are basis for R power 3. Let us check whether it is the linear combination or it generates a span. If so, we can say these are the bases. We shall see one by one. See the first problem, 1 0 minus 1 2 5 1 0 minus 4 3. This is what the question which is given. All the elements were taken in R power 3 because you are familiar with the term R power 3. R power 3 means we have to choose the element with the 3 each. A, B, C, to find that is linearly independent or linearly dependent. If linearly independent, we can talk about the term basis. Here let us checking linearly independent. We have to choose 3 scalars a1, a2, a3, and we will find a linear combination a1 into the first vector plus a2 into the second vector and a3 into the third vector. See, a1 into the first vector, a2 into the second vector, a3 into the third vector, which is equal to, let us consider it as 0 0 0. So now we shall see a1 into 1. So see, a1, it is nothing but a1 comma 0 comma minus a1 plus 2a2 comma 5a2 comma a2. Just multiply with the each entry. 0 into a3 is 0 minus 4a3 comma 3a3 equal to 0 0. This means coordinate wise addition is allowed. That means a1 plus 2a2 plus 0 equal to 0, or comma second term is 0 plus 5a2. So 5a2 minus 4a3 comma minus a1 plus a2 plus 3a3 equal to 0 comma 0, coordinate wise addition. From this we can say a1 plus 2a2 plus 0 a3 0, 5a2 minus 4a3 plus 0 a1 0, minus a1 plus a2 plus 3a3 equal to 0. This is what the 3 equation with the 3 unknown. You can use calculator. If you have FX 991 MS version means we'll go with the option. There you can see what about it. It is choose select equation, and there you can it will ask how many variables. If it is 3, you put 3, and then you have to feed what is the coefficient from the first equation. What is the coefficient of a1, a2, a3. Put equal and complete it, then b1, b2, b3. It will ask like that, c1, c2, c3. Just you have to enter the coefficients of each term. Finally you put an equal to 0. You will find all the unknowns, a1 what, a2 what, a3 what. In a single line itself you will find it. Since all the 3 unknowns were 0, automatically we can say the linear combination is linearly independent. If it is linearly if the set is linearly independent means we have a theorem, any linearly independent subset of V that contains exactly n vectors is a basis for V. So if it is n element, so the vector, if it is n elements, the vectors of order n which is linearly independent means the basis is n. Here is the vector with 3 elements because it is from r power 3, only 3 set of vectors. Automatically the basis for this r power 3 is, hence the set basis for r power 3 is 3. So that is what the question. Now let us see in the similar manner we can see the next question. It is to determine that the set is basis for r power 3. So if previously we saw all the 3 were the basis of r power 3. So in the similar way we can see, we can check whether it is linearly independent or not. If it is linearly independent, we can say these are the 3 which are the basis for r power 3. It is r power 3. To find the set is linearly independent or linearly dependent. So by choosing linearly independent, we can select 3 scalars a1, a2, a3 and form a linear combination. A1 into the first vector 1 minus 3 minus 2 plus a2 into the second vector minus 3 1 3 and plus a3 into the third vector minus 2 minus 10 minus 2 equal to 0. And check whether it is linearly independent means linearly independent or dependent. If dependent, we cannot talk about the term basis. If linearly independent means we can we can say yes, these are the 3 vectors which are also the basis of r power 3. For that we can solve. We will find out a1 not equal to 0, a2 not equal to 0, a3 also not equal to 0. Therefore the linear combination, the given set of vectors with the linear combination is not linearly independent, that is linearly dependent. If it is linearly dependent means we cannot tell these are the bases. So therefore since it is linearly dependent, so the given set of vectors are not the basis of the given vectors V. So it is not the basis for the given vectors B. What is V? R power 3. If it is if the given vectors are the basis of r power 3 means those vectors form a linear combination and the vectors should be linearly independent. But here is the problem, we have proved that it is not linearly independent, so automatically the given second set of vectors were not the basis for r power 3. Similarly, we can see this question. This is a problem with the polynomial. There are three set of polynomial. We shall check whether these are these in each case whether it is basis for P2 of R or not. See, P2 means polynomial with the maximum degree 2. Pn means polynomial with the maximum degree n. It is P2. The previous problem is r power 3. Now it is a problem with the polynomial. Let us check one by one. Let us check whether the following set of polynomials were linearly independent or not. If it is linearly independent, we can say yes, these are the basis for P2. If not, we can say it is not. So like that way we can check to find the set is the basis for P2 of R means first to find the set is linearly independent or not. For that we can choose A, B, C such that A into the first polynomial plus B into the second polynomial plus C into the third polynomial equal to 0. So multiplying we can find in the previous multiplying we can get what? Minus A minus AX plus 2AX square plus 2B plus XB minus 2BX square plus C minus 2CX plus 4CX square is equal to 0. Then we can write the terms with the higher powers, next higher, next smaller etc. So that we can write the first power with the x square term 2a minus 2b plus 4c into x square. The next term plus x into it is minus a plus b minus 2c, and the constant term were minus a plus 2b plus c. It is nothing but 0. It is 0 0 0 only, so we can call it as 0. So this means 2a, so it is, we can write it as 0 into x square plus 0 into x plus constant 0. So 2a minus 2b plus 4c equal to 0, minus a plus b minus 2c equal to 0, and minus A plus 2B plus C equal to 0. So that is what clearly given in the next slide, which is, yeah, this is this. So solving, we can find, or we can move with the particular case when we put a C with the 1, because an equation with the 3 unknown, A, B, C, 3 unknown with the 3 equation. Putting C as 1, C is equal to 1. Equation number 1 becomes minus A plus 2B minus A plus B minus 2A minus 2B. Solving, we will find out A and B. And then already we have chosen C as 1. Okay, solving, we can get A, B, C. So we can substitute these values in any one of the equation. 2 into A. What is A? Minus 5. So it is minus 10 minus 2 into B is minus 3. It is plus X. So it is minus 4. While putting A with the minus 5 and B with the minus C, this answer is minus 4. Yes, it is satisfied. So our values were correct. A, B, C are correct values only. Clearly C is arbitrary. So when we look at A, B and C, all the constants, all are constants of the linear combination, but we have proved that, or we got the values of A, B, C are all not equal to 0. If not equal to, so if the scalars of a linear combination values, scalars of a linear combination are not all 0, we can call that linear combination is linearly dependent. So we conclude that for this particular collection of polynomial, since it is not linearly independent, so those polynomials are not the basis for P3 of F. So in the similar manner, we can check the second problem also. First is polynomial, second polynomial, third polynomial. We can choose 3 scalars, A into minus A plus 2x plus 4x square plus B into 3 minus 4x minus 10x square plus C into this equal to 0. And then simplification, minus A plus 2ax plus 4ax square 3b minus 4bx minus 10bx square minus 2c minus 5cx minus 6cx square equal to 0. Then we can write similarly x square term, x term, 4a minus 10b minus 6c into x square plus x term where 2a minus 4b minus 5c into x, and the constant term where minus a plus 3b minus 2c equal to 0. So equating the coefficients, we will be getting, because here 4a, a plus 3b minus 2c is 0, it is in the first equation. 2a minus 4b minus 5c equal to 0 is in the second equation. 4a minus 10b minus 6c is equal to 0. We can consider it as 0, 0. 3 equations. Because our RHS is 0, this 0 can be written as 0 into x square plus 0 into x plus 0. So the coefficient of x square in the RHS is 0. Here the coefficient is 4a minus 10b minus 6c. So 4a minus 10b minus 6c equal to 0. 2a minus 4b minus 5c equal to 0. Minus a plus 3b minus 2c equal to 0. That's why we got these 3 equations. Solving, we can find a, b, c. While solving, we got the values as a, b, c. See, this is another way of checking, because without solving also we can find we can check whether it is linearly independent or not. We can we can choose those values as a matrix form. From the coefficient of the given equation, we can form a matrix which is called a coefficient matrix, and check whether the coefficient matrix is singular or not. Singular means determinant value equal to 0. Non-singular means not equal to 0. If it is equal to 0 means, if the determinant value is equal to 0 means it is the singular matrix. Singular matrix means singular. Equal to 0 means singular. Equal to not equal to 0 means non-singular. If the given matrix is non-singular matrix means automatically the coefficient form the equation as a linearly independent set, automatically we can come to the conclusion that the set of linear combination is linearly independent. For that we can check this with the singularity condition, that is we can check what is determinant of the matrix A. So I think people are familiar with this expansion of determinant. How do you answer? So this is minus 1 into 2 by 2 matrix, no? Or I can write here 2 by 2 matrix, minus 4, minus 5, minus 10, minus 6, minus 3 into 2 by 2 determinant, leaving that corresponding rows and column, 2, minus 5, 4, minus 6, then minus 2 into corresponding rows and columns, strike it and write the remaining, 2, minus 4, 4, minus 10. So the answer is minus 1 into minus 4, minus 6, that is 24, AD minus BC, it is 50, minus 50, minus 3 into minus 12 plus 20, minus 2 into multiply minus 20 plus 16, so that 24, so that is what here written, 24 minus 50 is 20 minus 26 into minus 1 minus 26, 3 into it is 8, 8 3s are 24, that is minus 24. The answer is 4, minus 4 into minus 2 plus 8. So the determinant of this value becomes 10. 10 means it is not equal to 0. If the determinant A equal to 0 means it is singular. If it is not equal to 0, non-singular matrix of order 3 is its rank. So automatically the matrix is a linearly independent, so that we can come to the conclusion that these three set of polynomials are the basis of P2 of R. So there are two examples we saw. One is not the basis. We have checked since those polynomial with the linear combination is not linearly independent, so that automatically those vectors are not the basis of the given polynomial set P2 of R. Just we have proved another problem with these polynomials or the linearly or the vectors making the linear combination with the linearly independent set. So automatically these polynomials are the basis of the given set P2 of R. So similarly we can see the last model of the problem, that is, let W denote the subspaces of R power 5 consisting of all the vectors having coordinators that sum to 0. So the vectors were u1, u2, u3, u4, u5, u6, u7, u8. There are 8 vectors were given. We can find a subset of the set u1, u2, etc. u8, it is not 3, u8. We can find a subset of the set u1, u2, etc. u8, that is the basis of the given set W. What is W? W is, it is 5 tuples. Let us see the proof. Let us consider u1, u2, etc. u8. Here u1 equal to minus 3 2, so omit u2. Here A into this plus B into this. Let us form a linear combination with the 5 scalars. A1 with one scalar, A2 with another scalar, is u1, u5, u6, u7, u8. We skipped with the, it was given like that. We can skip u1 is nothing but minus 3 u2. So let us omit u2. That's why u1, u4, u6, u6, u7. Only 5 entries we have chosen. So with the linear combination we got A into the first vector, B into the second vector, C into the third vector, D into the fourth vector, E into the fifth vector. Explicitly multiply with the each vector with the A, second vector with the B, third vector with the C, the fourth vector with the D, fifth vector with the E. Remove the bracket and choose the coefficient of A, B, C, D, E. You will find out these 5 equations. Solving these 5 equations in a matrix form, will let us find the rank using row and column operation, or you can solve your own way and we will find out the matrix with the upper triangular matrix. So using row and column row operation, we can find this augmented matrix as a upper triangular matrix. See, we matrix with the above diagonal entries are all 0 and below above entries are present and below diagonal entries are all 0 means it is called upper triangular matrix. So using row operation means we can add or subtract any two rows. We can multiply a scalar number with any two rows. The thing is we have to make below diagonal entries as 0. Below diagonal entries as 0. So here we got it using row operation. It was clearly mentioned in the sheet. So we got an upper triangular matrix. With this we can see equation number. So see here 1 2 3 4, there are 4 diagonals. It is 2 3 4 5 rows with the 5 columns. It is a square matrix with the 5 rows and 5 columns. We can see how do you check whether solving. So what about the row with the all entries 0? So this is the row with all entries, so we can omit it here. Remaining it is 4 by 3. So automatically the coefficient are A0, B0, C0, D0, E0. All the coefficient, because one whole row is 0. So these are the coefficients of A, B, C, D, E. Automatically we can say A0, B0, C0, D0, E0. All the scalars of these 5 vectors were 0. So automatically we can say this is the linear combination. Therefore U1, U5, U6, U7 are the basis of the given vector W. So now let us see the fifth problem. Find the basis for the following subspaces of F5. W1 is A1, A2, etc. A5 with the condition A1 minus A3 minus A4 0 and W2 equal to A2 equal to A3 equal to A4 and A1 plus A5 equal to 0. What are the dimensions of W1 and W2? We shall see. W1 W2 be the subspaces of F5. W1 equal to this with the condition. So let the vectors are taken as A1, A2 as some X, A3 as some Y, A4 as some Z, A5 as some W. Just we were choosing. And the condition which is given as A1 minus A3 minus A4 is equal to 0. That is X minus Y minus Z equal to 0. Because A3 is Y, A4 is Z, A1 is from this we can write A1 equal to A3 minus A4, A3 plus A4 going to the RHS, but A3 is Y, A4 is Z. That's why A1 becomes Y plus Z. So that W1 becomes A1, A2, A3, A4, A5 such that condition A1 is Y plus Z, A2 is X, A3 is Y, A4 is Z, A5 is W. This X can be X plus Z. This can be written as X plus Z. This can be written as 0, 1, 0, 0 plus Y 1, 0, 1, 0, 0. Z with the 1, 0, 0, 1, 0. W with the 0, 0, 0, 1. Only the last entry is 0, W. So removing the bracket you will find it. See, I can show you. This is nothing but 0 X then 0, 0, 0 plus Y 0 Y 0, 0 plus Z 0, 0, Z 0 plus 0, 0, 0, 0 W. By coordinate wise addition we can say 0 plus Y plus Z. So you will be getting Y plus Z, comma X plus 0 plus 0 plus 0, that is X. Third coordinate is 0 plus Y plus 0 plus 0, so that is Y. Fourth coordinate is 0 plus 0 plus Z plus 0, that is Z. Fifth coordinate is 0 plus 0 plus 0 plus W, that is W. So therefore this can be written as this form. Correct? So that's why this y plus z can be y plus z comma x comma y comma z can be written by this form. Then the basis is 0 comma 1 comma 0 0 plus 1 comma 0 comma 1 comma 0 0 comma 1 0 0 1 0 comma 0 0 0 1. Therefore 1 2 3 4 there are 4 bases. These are the 4 bases because while making this with a linear combination, all the coefficients were 0 only. So it is the linearly independent set, because already we have proved that a1 a3 a1 is nothing, a2 is nothing but x, a3 is nothing but y, a4 is nothing but z, a5 is w. Automatically all the scalars were 0. So it is a linear combination. Therefore these are the bases of the given set. But it is how many dimension, how many 1 2 3 4. Therefore the dimension of this w1 set is 4. So this is the way you have to write basis and dimension of the given problem. So there are 2 parts in the question. W1 is over. Similarly the basis of W2 are as follows. W2 is collection of A1 A2 A3 A4 A5 belongs to F5 tuple and with the condition A2 A3 A4 equal and A1 equal to minus A5. Consider A4 as x, A5 as y, A1 as minus y, and A2 A3 A4 as x. So you will be getting W2 as minus x, A1 is what? Minus y, A2 is x, A3 is x, A4 is x, A5 is y. Then this can be written as, see, this is what by coordinate wise addition, this is x, 0, x, 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 0 plus minus y 0 0 0 y. So what is this coordinate wise addition? We can write this as 0 minus y, it is minus y, x plus 0 is x, x plus 0 is x, x plus 0 is x, 0 plus y is y. Okay, so therefore the basis is 0 1 1, the linear combination also 0, the scalars were 0. Therefore this is the basis. First 1 0 1 1 1 0 minus 1 0 0. These are the 2 bases of the given set W2. And how many? There are 2. Therefore since how many, the dimension is the number, finite number, how many, the count is the dimension of the, if the count of the bases is called the dimension. Here the bases are 2, therefore the dimension is 2. This is what the answer of the problem. So with this I conclude the episode. So please stay and subscribe and get the coming videos also. Thank you. All the best.
இந்த வீடியோ உங்களுக்கு பிடிச்சிருந்ததுன்னா லைக் பண்ணுங்கள், ஷேர் பண்ணுங்கள். இதே மாதிரி நிறைய வீடியோஸ் பார்க்கணுன்னா டார்ஜில் லேர்னிங் ஹப்பை சப்ஸ்கிரைப் பண்ணுங்கள். மறக்காமல் அந்த பெல் ஐக்கானையும் கிளிக் பண்ணுங்கள். தேங்க்யூ.